Today we solve some exercises covering all chapters of the course. So first I will start with exercises where you have questions and you have to answer by means of computations or graphs. And later in the second part of the lecture we will have questions that have just true or false response. Okay, the first exercise is a classification problem. Here we have a table with training data, 6 observations, 3 predictors, x1, x2, and x3, and one qualitative response variable. So this is the label that is assigned to our training data. The label, as you can see, can only be red or green. And assume that we would like to use this data set to predict the label when all the 3 predictors are equal to 0, and we want to do this by means of k nearest neighbors. So the first step is computing the Euclidean distance between each observation and the test point x1 equal to x2 equal to x3 equal to 0. So here I have the observations and I have to compute an Euclidean distance. So here you have 0 squared plus 3 squared plus 0 squared and everything under the square root, and therefore the result is 3. Here I have the square root of 2 squared. Here the square root of 1 plus 3 squared, this is 3.16. Here the square root of 1 plus 2 squared, 2.23. The square root of 1 plus 1, so the square root of 2, 1.41. And finally the square root of 1 plus 1 plus 1, the square root of 3, and this is 1.73. So this is easily done. Okay. Now, what is our prediction with one nearest neighbor? This means that I have to consider, to find the observation that is closest to my x, and my x is 0, 0, 0, and then I will label the new point x equal to 0, 0, 0 using the label of the nearest neighbor. So what of these observations is closest to the origin? As you can see, it is 1.41, so it is the fifth one, which is green, and therefore the set, I call nk the set of k nearest neighbors, so this is a set of k elements. So here k is equal to 1, so one element, this is 5, it is green, it's labeled, and so this is the answer. Second question, third question, what is our prediction with k equal to 3? In this case, I have to find the 3 nearest neighbors. I again look at the table here, and I have 1.41, of course, 1.73, and 2. So the observations are number 2, 5, and 6. Okay, these are the observations. I have used colors to report their labels, and I see that have 2 red labels and 1 green label, so red wins, and this is my prediction for 3 nearest neighbors. Final questions. If the Bayes decision boundary in this problem, Bayes decision boundary is to say the best possible classifier, if the Bayes decision boundary is highly nonlinear, would we expect the best value for k to be large or small? Okay, highly nonlinear, okay, there is an h missing here, means that we need a flexible classifier, of course. And therefore, if you want to have more flexibility, you should use nearest neighbors with a relatively small number for k. Because if you use a very large k, you're going to regularize and you won't be able to follow a highly nonlinear decision boundary. That's all. Next exercise. So we have 4 parts, and for each of them you should indicate whether you expect to be better a flexible flexible statistical learning method or an inflexible one, and we should justify the answer. First, the sample size is extremely large and the number of predictors P is small. Okay, in this case I could go for a flexible learning method. Why? Because I have enough information to estimate the parameters. So I have n that is extremely large, so I have a lot of data, and just a few parameters. This means that the number of data for each parameter is more than sufficient, and therefore I can exploit all the flexibility that the P parameters can give to me, and the predictors. I can exploit all the information that the predictors give to me, because having all this information I can afford a certain degree of flexibility. B. The number of predictors P is extremely large and the number of observations is small. In this case, I would prefer an inflexible method, because here information is scarce, because I have to estimate a large number of parameters, because I will have at least one parameter for each predictor, for instance, and I do not have many data. In some cases, it could even happen that the number P of predictors is larger than the number of observations, in which case you should use some shrinking method, for instance, like the lasso of the ridge. So information is scarce, especially if compared to a number of parameters that grows with P, of course. Therefore, I cannot afford a flexible method, because there is a very concrete risk of overfitting. So in this case, inflexible should be better. C. The relationship between the predictors and response is highly nonlinear. In this case, I would go for a flexible method, because I need flexibility in order to account for the nonlinear response. For instance, I could use linear regression, but if the actual response is nonlinear, the predictions of linear regression could be highly biased. So in this case, if possible, I would go for a flexible method in order to follow the nonlinearity of the response. D. The variance of the error terms, i.e. sigma square equal variance of epsilon, this is the variance of the irreducible error, is extremely high. This is a context where I would use an inflexible method. I would say that the signal in this case is buried in noise, because you have so much noise, and therefore if the data are that noisy, I believe that you are not able to reliably estimate a very complex model. So if there is so much noise in the data, you would better adopt simple models in such a way you can at least reliably estimate their parameters without excessive uncertainty. Next, in order to obtain better intuition about ridge regression, I will not discuss the lasso here. Consider a special case where the number of data is equal to the number of predictors, and X is a diagonal matrix with ones on the diagonal and zeros elsewhere. This means that X is the identity, of course. To simplify the problem, we assume that we do not have an intercept, And in this case, if we use the least squares, this would be the cost function. These are the residuals, the sum of squared residuals. And of course, the least square solutions is just beta hat j equal yj. And in this setting, on the other hand, a ridge regression amounts to minimizing this cost function. Okay, so you have the usual sum of squared residuals, and here you have the shrinkage penalty on your parameters. Under these assumptions, you are asked to compute the expression of the ridge estimator. So we would like to see how we can write down the ridge. So matrix X is the identity of order n, and Y is the vector of the observations, and the ridge estimator is the value of beta that minimizes this cost function. And we have already seen here is the squared norm of the residual vector. This is the norm of the parameter vector squared. And we have already seen that this can be written in this way. Let's call this j of beta. This is the cost function. And the nice feature is that here you have n independent minimization problems, because here I have the sum, but as you can see, there are n problems, one for each I, and they do not talk to each other, so they are completely independent. So I can just solve for each value of I a minimization problem, and I will find eventually my ridge estimator. This is a simple minimization problem because they are quadratic, but well, I just take the derivative with respect to beta I. This is quite simple. So here is the computation, minus 2y sub I minus beta I plus 2 lambda beta I. This should be equal to 0, and I will find that the candidate point is beta I star yi sub over 1 plus lambda. And it is immediate to see that the second derivative is greater than 0, so these are global minima for each I, and I put together all these solutions and I find that the ridge estimate has the structure is just y over 1 plus lambda. This is nice. So you see that if the regularization parameter lambda is equal to 0, you just have beta hat ridge equal to the data. And this is consistent with the fact that this is the least square solution. So this is something that you already know, that if the regularization parameter is equal to 0, you retrieve the least square solution. And on the other hand, when you increase lambda, you are going to shrink the value of the parameters, and as lambda goes to infinity, everything is going to 0 in the end. So if lambda goes to infinity, then all the parameters will tend to 0. Okay. A question about classification. Suppose that we take a data set, divide it into equally sized training and test sets, and then try out two different classification procedures. First, we use logistic regression and get an error rate of 20% on the training data, okay, and which could be good, rather good, and 30% on the test data. Next, we use one nearest neighbors and get an average error rate. Okay, attention. This is an error rate averaged over both test and training datasets of 18%. Based on these results, which method should we prefer for you to use for classification of new observations? This is rather tricky, apparently. Because here you have 20% on training data and 30% on test data. And here you have just 18% on all the data. My answer, but think about this if you have a different one, of course, is that I would use one nearest neighbor, and this is my reason. The reason is that if I use k nearest neighbor, I'm not actually estimating parameters, so I just have a rule, and very simply I take the k nearest neighbors and then I look at their labels, and I just choose the label that has the majority within this set of neighbors. And since I have no parameters to estimate, I can just put together all the data, both the training and the test data that I was using for logistic regression, but now I can take all of them at the same time and compute the average error rate. And in some sense, I think that this set of all the data plays the role of a test error rate. So because I don't actually need the training data. And therefore, this 18% is representative of the actual performance of one nearest neighbor. So I would go for one nearest neighbor in this context. Let's discuss bias variance decomposition. And we should draw a sketch of the typical curves of bias, variance, training error, test error, and irreducible error in a single plot as we go from less flexible to more flexible approaches. It's like having lambda, the regularization parameter, the shrinking parameter, and having lambda going from 0 to infinity, for instance. Okay, here they ask from less flexible to more flexible. I would go the other way from yes, no, okay. I would go from more flexible, lambda equal to 0, to less flexible, lambda equal to infinity, but doesn't change anything because the x-axis will represent the amount of flexibility, and the y-axis will be the value for each curve. There will be 5 curves, and we should explain why they have a certain shape. Okay, this is similar to another exercise that we had already discussed. Anyway, this is the plot. Here I'm using lambda, the shrinking parameter, and therefore for lambda equal to 0, I'm not performing any regularization, so this is more flexible, okay? And as lambda increases, this becomes less flexible. And here I have the curve, so here I have the reducible error, this is the variance of the reducible error, and of course it doesn't change, so it's constant, because it has to do with the error committed by the regression function, the conditional expectation of the response given the predictors, and this is a kind of ideal solution. So of course it is not affected by lambda, and it is constant. Then I have the variance of the estimator, and the variance of the estimator when I am very flexible has the highest value, but when I reduce flexibility, this is going to decrease, and this is what happened to variance. And this is the opposite for bias. Here I have the curve of squared bias. When I am more flexible, I can follow the response function and the regression function, for instance, and of course, I have a little bias, but if I reduce flexibility, the price to pay for this is that bias will increase. At this point, if we look at the test error that I've written this way as the expectation of the squared estimation error, This will be the sum of these three, the reducible error, the variance and the squared bias, the variance and the squared bias. And there will be a trade-off, because at the beginning I take advantage of the reduction of the variance, and so it goes down. But after a certain point, it will usually happen that the increase of the squared bias makes the test error to increase as well. So there will be a kind of optimal trade-off usually here, and this is the optimal choice of the shrinking parameter. And of course I don't know the real red curve, so I will need methods to estimate it and or finding to find its minimum point, or at least approximate the value of lambda that corresponds to this minimum. Finally, I am considering what's happening with training, and when I have training data and I am not flexible, I will not be able to follow the training data, so I will have a large training error. But when I increase flexibility of the method, I will have that the training error gets smaller, and so this is it. But I should not be fooled by this, because I'm interested in the test error. So here it seems that I have a very good result, but as a matter of fact, I'm learning the noise, the noise in the training data, and if I take new fresh test data, they will have a different noise, and therefore the performance could be anything but good. So this is the real performance. This is what I see in the training data, but on the test data, the story is completely different. Question about differences between linear discriminant analysis and quadratic discriminant analysis. Some questions. So, if the base decision boundary is linear, do we expect linear discriminant analysis or quadratic discriminant analysis to perform better on the training set? And what on the test set? Okay, what's the possible answer? Training set. I would say that QDA is going to perform better because it is more flexible. You should remember that in linear discriminant analysis, you are assuming that all the classes have the same variance matrix in the model for the predictors. So when I'm performing discriminant analysis, I am assuming a distribution model for the predictors, and for LDA, the variance matrix, I assume a Gaussian model. The variance matrix is the same for all the classes, while I have different variance matrices if I am using QDA. This means that I have more parameters, more degrees of freedom, and therefore I'm more flexible, and I expect that this flexibility is exploited in the training phase to reduce the error rate. On the other hand, when I move to the test set, the extra flexibility could not be an advantage, of course. Why? Because if the decision boundary is linear, a linear discriminant analysis is sufficient to obtain linear decision boundaries, and therefore the extra parameters could be used to learn the noise again. So we have a kind of over-parameterization for QDA, and therefore the advantage on the training set becomes a disadvantage on the test set, where LDA should do better because it has not superfluous parameters. Question B. If the base decision boundary is nonlinear, do we expect LDA or QDA to perform better on the training set and on the test set? In this case, LDA is not adequate because it cannot give you a decision boundary that is nonlinear. It is piecewise linear, the decision boundary that we will find by LDA. Therefore, in general, I would expect QDA to perform better on both sets because LDA cannot follow the decision boundary. In this case, I really need the extra flexibility of QDA. Final question. In general, as the sample size n increases, do we expect the test prediction accuracy of QDA relative to LDA to improve, decline, or be unchanged? I would expect that it is going to improve because if QDA suffers from overparameterization, this problem is going to improve as the sample size increases. If you don't actually need QDA, but LDA is sufficient, but you have really plenty of data, then the variance matrices of your model, of your predictors model in QDA will get closer and closer to each other. So in the end, you find identical or almost identical variance matrix, just learning this from the data, while LDA knows it from the start because it is an assumption of the method. And on the other hand, if you do not have an overparameterization problem, with the increase of the data, QDA will get closer and closer to a better approximation of the decision boundary. So if you have more parameters, your performances, I guess, are going to improve when the sample size increases compared to the performances of a simpler model with fewer parameters. Okay, here we have some scenarios in which we have a problem, a learning problem that is described, and we are asked to say whether this is a regression or classification problem, and also to provide values of n and p. N is the number of observations and p is the number of predictors. First problem, we collect a set of data on the top 500 firms in the United States, and for each firm we record profit, number of employees, industry, and chief executive officer salary, the CEO salary. We are interested in understanding which factors affect the CEO salary. Okay, this is a regression problem because we would like to work out a predictor of the CEO salary, that is a continuous variable, and the number of observations are my 500 firms, so n is equal to 500, and the number of predictors are profit, number of employees, and the type of industry. This will be a categorical variable, of course. So this is the answer. B. We are considering launching a new product and wish to know whether it will be a success or a failure. We collect data on 20 similar products that were previously launched. For each product, we have recorded whether it was a success or failure, price charged for the product, marketing budget, competition price, and 10 other variables. This is a classification problem because the response is success or failure. The number of observations is given by the number of previous products, 20, and the predictors are price, budget, competition price, these are 3, plus 10 other variables, so 10 plus 3, 13. Of course, I am not counting this success or failure, that is the label, the classification label, because this is the response variable, as a matter of fact. C. We are interested in predicting the percentage change in the USD, United States dollar versus euro exchange rate in relation to the weekly changes in the world stock markets. Therefore, we collect weekly data for all 2012. For each week, we record the percentage change in the USD/euro, the percentage change in the US market, the percent change in the British market, and the percent change in the German market. Okay, here again we have a regression problem because we are going to predict the percentage change that is a continuous variable. The number of observations, since we collect weekly data for an entire year, will be 52, that is the number of weeks, and the number of predictors will be the percent change in the US market, 1, percentage change in the British market, 2, and percentage change in the German market, 3. The percentage change in the USD/euro is just the response variable and should not be counted, of course. Okay, suppose that we use some statistical learning method to make a prediction for the response y for a particular value of the predictor x. Describe how we might estimate the standard deviation of our prediction. Here we have to note that the statement is very generic, so I don't know what learning method I've been using, and therefore I think that the best response is suggesting a technique that is very general. A technique with this feature is the bootstrap. Of course, if I had an explicit formula for the predictor, then I could make assumptions on the noise in the training data, and I could try to propagate the noise also analytically, but this will work only in special cases. Instead, if I have a general learning method, I need a very general purpose technique. This is, as I said, the bootstrap. So I can generate k bootstrapped data sets. You recall that bootstrapped data set is obtained by sampling with replacement. Okay, so I just sample n observations from the original training set. But every time I draw a sample, I replace it again and I repeat the drawing. Okay, and I generate k bootstrapped datasets on which I train my predictor, and then the trained predictor is applied to obtain my prediction y hat j. This j refers to the jth bootstrapped dataset. In the end, I will have capital K predictions, and therefore I will be able to compute the sample variance from this data. And therefore, I will have a variance, and taking the square root, I will have a standard deviation for my prediction.